You ever see a quadcopter just hanging there in midair, perfectly still, and wonder, how on earth is it doing that? I mean, it seriously looks like magic. But it's not. It's actually this beautiful symphony of physics and, you guessed it, a whole lot of math. So today, we're going to pull back the curtain and really unpack the science that gives these drones their incredible stability. So let's start with that big question right there. How does a machine with four propellers spinning like crazy manage to balance so perfectly against gravity, against the wind? Well, the secret isn't just in the motors and the plastic. It's deep inside the software, built on an incredibly detailed mathematical understanding of the drone itself. All right, first things first. Before a computer can even dream of flying a drone, the engineers have to understand every single physical force acting on it. It's kind of like creating a complete inventory of every push, every pull, and every little twist that drone is going to experience once it's up in the air. And this table here gives you a little taste of just how complex we're talking. I mean, it's not just one or two things. You've got the obvious one, right? Gravity, pulling it down. But then you have all these wild aerodynamic effects from the air rushing over the propellers. You've got inertial countertorques that happen every time a motor speeds up or slows down. And you've got these really powerful gyroscopic effects that are constantly trying to resist any change in direction. Every single one of these has to be accounted for. No exceptions. So, once you've got a handle on all that physics, how do you actually translate it into something a computer can understand? This is where we get to the real heart of it all, system modeling. The best way to think about it is like you're creating a digital blueprint, or maybe a super detailed rule book for exactly how the drone is supposed to behave. Yeah, at its core, a system model is basically a set of mathematical equations that perfectly describes the drone's physical reality. It's the special language engineers use to teach a flight controller the laws of physics, but specifically as they apply to that drone. It's the drone's own personal physics rulebook. But trying to model every single atom in vibration would be totally impossible. So engineers have to start with a few smart simplifications to make the problem manageable. For example, they'll assume the drone's frame is perfectly stiff, that it's symmetrical, that the propellers don't bend, and that forces like thrust and drag follow a nice, predictable formula. This creates a really solid foundation to build the rest of the model on. Okay, so with those basic assumptions in place, engineers can create their very first model. Let's call this the first draft of our drone's physics rulebook. It's a bit simplified, sure, but it's a functional start. One popular way to create this first draft is with something called the Euler-Lagrange model. Now, don't worry, we're not going to get lost in the weeds with the equations here. The main idea is actually pretty elegant. It basically describes how the drone moves by just looking at the total energy in the system. Its kinetic energy from moving around and its potential energy from how high it is off the ground. But here's the catch. An energy-based model is a fantastic start, but it's really like a simple sketch. It captures the basic idea, the general shape, but to build something that can fly complex missions in the real world with wind and all sorts of variables, well, for that, you're going to need a much more detailed engineering blueprint. So how do we get from that simple sketch to the detailed blueprint? Well, engineers use a much more advanced approach, often called the Newton-Euler model, to capture all those real-world complexities that the simpler model just ignores. And one of those key complexities is the gyroscopic effect. Think about it. The propellers on a drone are spinning incredibly fast, thousands of times a minute. This creates a powerful stabilizing force, almost exactly like a spinning top, that desperately wants to stay upright. This advanced model includes these forces, which are absolutely critical for predicting how the drone is going to react when it tries to tilt or turn. The Newton-Euler model also goes way, way deeper into aerodynamics. Instead of just assuming the forces are always the same, it understands that things like thrust and drag actually change depending on what the drone is doing. It knows that the forces are different when the drone is flying forward at full speed compared to when it's just hovering. This makes the model so much more accurate during tricky maneuvers. And check this out. Here's a really fascinating real-world effect that has to be modeled. It's called ground effect. So when a drone gets really close to a surface, like when it's about to land, a cushion of high-pressure air builds up beneath it, which actually gives it extra lift. For a drone to pull off a perfectly smooth autonomous landing, its digital blueprint has to know about this and account for that sudden change in thrust. Pretty cool, right? So let's bring this all home. We've gone from these abstract forces to complex equations to a full-blown flight simulator.
But how does all of this connect back to the incredible things we see drones do in the real world every single day?
Well, it all boils down to this logical path right here on the screen. It's a journey. You start by understanding the basic forces. You build a simple model. Then you level up and create a much more realistic one. You test and perfect everything in that safe virtual simulator. And then, finally, you can achieve intelligent, autonomous flight in the real world. Because the result of all this work is that the drone has a perfect internal understanding of its own physics, that digital blueprint we talked about. And when it has that, it can start to make its own smart decisions. This rigorous modeling is exactly what allows drones to perform these complex tasks, like landing on their own, holding a position perfectly, and even dodging obstacles all by themselves.
And that leaves us with one last big thought. This whole process, really, is about creating a more and more perfect mathematical mirror of reality. So as these digital blueprints become even more flawless, even more accurate, what new capabilities are we going to unlock? What amazing tasks that seem like science fiction today will become totally routine for the autonomous drones of tomorrow?